As a simple application of LRC circuits, we are going to look at this problem. So you have a light bulb, a 50 watts light bulb, but it was designed to be used in US. So therefore, when you plug into a wall plug that has a 110 volts of EMF, it just consumes 50 watts. That's the case in US, of course, but in Turkey, of course, we are using 220 volts AC. So as a result, you cannot use this thing directly. So you have to do something else. So let's then try to understand what happens if you plug into a 220 volts of AC directly. So what happens to your light bulb? Just keep in mind that what you're doing in here is to basically doubling the amount of the potential drop on the light bulb. And since the power depends on the square of this potential difference, you would expect that this 200 watts of power goes into the light bulb in such kind of a situation. So if it lights up, then it should be at least 4 times brighter than normally the normal brightness that it should have. Unfortunately, of course, the light bulbs are not simple linear devices like that. So as a result, they are not designed to work with these conditions. So most of the time they are going to blow up because that power would be too much for them. So as a result, we cannot use this kind of a scheme. So what happens is that it's not even a scheme actually. So you're just directly plugging to the wall. So what can you do? You can do this. You can just connect this light bulb to another device and then connect these to the wall plug. Right? So as a result, if you choose the parameters of that unknown device correctly, then you can perhaps use your light bulb with the same power. So as a result, somehow choose this device in the best possible way so that your light bulb in here uses 50 watts of power. What can that device be? I'm just going to consider simple choices. It can be a resistor or an inductor or a capacitor. So in each case, of course, we need to find the corresponding parameter, the resistance, inductance, and the capacitance. So I'm going to look at these 3 cases, and then at the end, we can perhaps compare the advantage of any one of them. So before going further, so let's just talk about the possible value of the resistance of the light bulb. So you can see that in here, for example, what might be the current that's passing over the light bulb under normal conditions. Basically, to be able to find this, you just need this power formula. Of course, this power is equal to the RMS value of the EMF multiplied with the RMS value of the current. Here, of course, I'm using EMF, but that's essentially the potential drop on the resistor. But obviously, if you just connect it to the wall plug, that would be the EMF would be equal to the potential drop on your light bulb on your device. So in all of these cases, whenever people talk about these potential values or the powers and things like that, they are assuming that they are using AC, and all of these voltage values are RMS values. So as a result, whenever somebody says it's, the voltage is 110 volts, this is the RMS value. So therefore, the RMS value of the current should satisfy that equation. Their product is equal to 50 watts. Again, remember that this is just the average power. It's not the instantaneous power. Instantaneous power is something that we never need. So the RMS value of the current would be 110 volts divided by 50 watts. It's just the opposite way. Sorry. So it is 50 watts divided by 110 volts. So that's going to be 0.45 amperes. So as a result, if I just consider as a simple resistance, so in that case, the resistance would be the RMS EMF divided by the RMS current. So that's 110 volts divided by 0.45 amperes. That's going to be 240 ohms. So let's simplify the problem. Let's just think of this light bulb as a simple resistor. So as a result, I don't know, if I change the potential drop on the light bulb, the current increases by the same proportional amount. All right, let's just think about it like this. So I'm also going to call this as light bulb resistance. Let's just remember this value because this is the one that we are going to use. So what happens, all right, so under normal working conditions, therefore, the amount of, let's say it like this, the amount of the voltage drop on the light bulb should be 110 volts, and the amount of the current that must be passing over the light bulb should be 0.45 amperes. So under these conditions, 50 watts of energy goes into the light bulb. So as a result, it works normally. So as a result, in here, therefore, I have to place something in here such that first, the amount of the current that's passing from the circuit should be 0.45 amperes. And so therefore, that's equivalent to what I'm going to say now. So the potential drop on the light bulb will be 110 volts. Right? So as a result, either I use this information or that information to actually solve for the circuit. But let's go over with the current. So the RMS current in that situation is equal to the RMS value of the EMF that I use divided by the impedance of the whole circuit. So this time I need to use an impedance because I don't know what this thing is. It might be an inductor or a capacitor. So in that case, it's a reactance. It has a reactance. So together with this resistance in here, the circuit is going to have some properties, but I can describe these properties by that impedance in here. Whatever. So I want that under 220 volts of RMS EMF, I should use an impedance value so that the current is still 0.45 amperes, which means, I mean, when I double the EMF, somehow the current remains the same. So that means the impedance of the circuit should be equal to 2 times the resistance of the light bulb. So that means 480 ohms. So I have to choose this device in such a way that somehow the whole circuit has an impedance which is twice the resistance of the light bulb. So I think this is the starting point that we should use. So with this, of course, we can simplify the analysis of all the other situations. So I'll start with this scenario where I connect a resistor. So this is the first situation. So there is an unknown resistor that I should place in here. So this is a light bulb, but let's just express it as a resistor in here. So the impedance of that circuit is just the sum of the resistances. So that's just the resistance, of course. And we want this to be equal to twice the resistance of the light bulb. So therefore, I need to use a resistance which is exactly equal to the resistance of the light bulb. All right? So this additional device should have a resistance which is 240 ohms. Okay. So in this case, of course, the current in the circuit would be, all right, I'll just cut the story short. So therefore, this is 0.45 amperes. So in that case, what happens is that light bulb uses, let me write it down like this, the average power, which is current squared multiplied with the resistance, but this is going to be 50 watts, as you well know. But some of the heat will also be dissipated on this additional resistor you have added. So therefore, I don't know, let me call this as P device. So that's also an average power. So I have to multiply the square of the same current with the resistance of that thing, but it has the same resistance, so therefore this also uses 50 watts of power. So therefore the total power used, let's say it like this, total used is 100 watts. So in US, of course, it consumes 50 watts of power, but here, unfortunately, you have to use more than 50 watts. It's actually double the amount. So as a result, it's going to cost you more in terms of the electricity bills. So basically, the EMF device should be supplying this 100 watts of power. Okay. So next scenario, what happens if I connect an inductor? And what should be the inductance? All right, so that's the light bulb again. So in that case, let's just, I don't want to draw the phasor diagram, but it was this kind of a situation. There's this current in here. There's a potential drop on the light bulb, which is basically the potential drop on a resistor. So therefore, it is in phase with the current. And there's a potential drop on the inductor. And somehow the EMF is equal to, let me erase this, sorry about that. I'm going to use a different color now. So the EMF would be just the vector sum of these two. So the EMF would be a vector like that. So this has a given magnitude. EMF has a given magnitude. The current has a given magnitude. So as a result, somehow I have to adjust the values of this VL. In any case, but of course we know that the impedance in that case is equal to, let's start with this thing actually. I'm just going to write this thing once. So EMF is equal to the square root of VL squared plus V bulb squared. So the same kind of a relationship is valid between the impedance and the reactance of the inductor and the resistance of the light bulb. All right. So we want the impedance to be have a resistance of 2 times R bulb. So this then implies that somehow I have to adjust the value of the impedance to be equal to the square root of 3 of the resistance of the light bulb. How much is that? I just computed this somewhere. So it appears that this is around 420 ohms. It is less than twice the resistance of the light bulb, which is 480 ohms. But still, it is some magnitude. So this basically, the function of the inductor in here is to decrease the amount of the current that is passing over the circuit. So let's see how much inductance I need for that. So I know that the inductive reactance is equal to omega times L. And here omega is 2 pi times the frequency. And we know that the frequency in our circuits is 50 hertz. So that means this is 100 times pi. So therefore this is like 314 radians per second. But I'm using two significant figures. So therefore I'm just going to write 310 radians per second for that. Okay. So inductive reactance is 420 ohms. Angular frequency is 310 radians per second. So inductance should be like that. So the inductance therefore is the ratio of these two numbers. And it appears that this is equal to 1.3 Henry. Okay. So this is the answer to the question. So what's the value of the device parameter? The inductance of the inductor should be 1.3 Henry. All Alright, so let's just then erase this unnecessary figure because I need to talk about the power. How much power is used by the bulb? It's going to be the same again, so the same calculation actually. So this part never changes because this is actually one of our restrictions. The light bulb should use 50 watts of power, that's okay. How much the inductor use? The device in here, so it's 0. So therefore, the amount of the power that is supplied by the EMF device, that's basically the total used, is equal to 50 watts. So in here, of course, you save from electricity bills. So you need to use 50 watts on the light bulb, and that's the amount of the energy that you spend. As a result, this is kind of better than using a resistor in here. So if I use a resistor instead of an inductor, that resistor will consume energy, and that means money. But if I use an inductor, then I don't need to consume any energy. Obviously, of course, all inductors have some internal resistance as well, but I'm just ignoring these kind of things. So what happens if I use a capacitor in here? So let's also look at this. Right, so that's again the light bulb. So we have a capacitor in here. In that case, there's a capacitive reactance, so that's Xc squared plus R bulb squared. Again, we want this impedance to be equal to 2 times R bulb. So therefore, the reactance should again be square root of 3 times R bulb. So therefore, this is 420 ohms. But in this case, Xc is equal to 1 over omega times C. So that means 1 over 310 radians per second multiplied with the capacitance. So that means capacitance should be equal to 1 over 310 multiplied with 420. Let me put a cross in here. So it appears that this is equal to 7.6 times 10 to the minus 6 farads, unit is farads, but we just use the microfarad value, microfarad unit. It's kind of more practical. So the capacitance should be 7.6 microfarad for this to happen. So again, we have a similar situation in here. The power used by the light bulb, I don't want to write down the details in here, is 50 watts now. Average power used by the capacitor is 0. Again, assuming that the internal resistances of the wires and things like that can be neglected. So therefore, the total energy that you use from the mains electricity is the total used is again 50 watts in here. So as a result, it appears that it is better to use for, let me pass to the second page in here. All right, so we could use a resistor or an inductor or a capacitor. If I connect a resistor in series with the light bulb, of course, there's always heat produced in here, and this is something undesirable. So as a result, it's always a better choice to use an inductor or a capacitor in there. And of course, since you know how to compute the reactances and the impedances, you can actually compute the parameter values that you need to use.